Great question. When an acid and base combine, they create a salt through neutralization. The base is your source of the positive ion. It provides the metal cation. The acid contributes the negative ion, which is the anion. Think of it this way. Bases contain metals like sodium or potassium that become positive ions, while acids like HCl or H2SO4 release their negative parts like chloride or sulfate ions. Together, these ions bond to form the salt. So the base gives you the positive charge, and the acid gives you the negative charge. Now let's dive deeper into what actually happens at the molecular level during neutralization. When a base accepts a hydrogen ion from the acid, it gains positive charge. But here's the key. It has to release its original metal cation to make room. So the base ends up contributing that metal cation, like sodium. Meanwhile, the acid donates the hydrogen ion away, which means it loses positive charge and leaves behind the negative ion, like chloride. That's why we get NaCl, sodium from the base, chloride from the acid. All right, everyone, here are our learning objectives for section 14.3. We're diving into acid-base chemistry, and we need to accomplish two key things. First, you'll learn how to identify conjugate acid-base pairs. These are molecules that differ by just one proton, and they're fundamental to understanding how acids and bases work together. Second, you'll develop the skill to predict what products form when acids and bases react with each other. These two objectives build on each other. Once you understand conjugate pairs, predicting reaction outcomes becomes much more straightforward. Let's get started. Now, we're translating those learning objectives into concrete success criteria, what you'll actually be able to do by the end of this section. Your first goal is to look at a complete acid-base reaction and pick out all four players, the original acid, the original base, and their conjugate partners that form as products. Your second goal is to take any acid and base combination and predict what salt and water form when they neutralize each other. These are your checkpoints for mastery. Here's the key insight. Bronsted-Lowry theory defines acids and bases by what they do. Acids donate protons, bases accept them. When we write an acid-base reaction, a proton physically moves from the acid molecule to the base molecule. By tracking exactly where that H+ goes, we can spot the conjugate acid-base pairs on both sides of the equation. This tracking skill is essential because it reveals the dynamic nature of these reactions and helps us understand why they reach equilibrium. Now let's define exactly what we mean by conjugate pairs. A conjugate acid is what you get when a base grabs that proton. It has one more H than the base did. A conjugate base is what's left behind when an acid donates its proton. It has one fewer H than the original acid. In our water reaction, H3O- is the conjugate acid of water, and A- is the conjugate base of HA. They're always paired because they differ by exactly one proton. This relationship is how we verify we've identified the pairs correctly. Here's a practical reference table showing real conjugate acid-base pairs you'll encounter in chemistry. Notice the pattern. Moving down the left column to the right column, each acid loses one proton to become its conjugate base. Look at HCl becoming Cl- or NH- becoming NH3. Some species appear twice. Water can act as both acid and base, and HSO4 acts as an acid toward sulfate, but as a base toward H3O-. This table is your toolkit for recognizing conjugate pairs in any reaction. Now let's apply what you learned. I'm giving you 3 conjugate acid-base pairs, but some boxes are blank. Your job is to fill in the missing information. For each row, you have either the acid or the base provided, and you need to determine its conjugate partner. Remember, an acid loses a proton to form its conjugate base, or a base gains a proton to form its conjugate acid. Use that reference table from the previous slide as your guide. Think about what happens when O- accepts a proton, or when HCl donates one. This is the fundamental skill for predicting acid-base reactions. Now it's time to practice. Look at each reaction and identify the 4 key players. In the first reaction, NH donates a proton to become NH3, so NH is the acid and NH3 is its conjugate base. Meanwhile, CN- accepts that proton to become HCN, making CN- the base and HCN the conjugate acid. Apply this same logic to the other two reactions. Remember, the acid is always on the left side losing a proton, and the base is what accepts it. Look for which species gains or loses one hydrogen and one charge to find conjugate pairs. Great, now you're testing yourself on the other two reactions. For the second one with CH33N and water, notice water is the acid donor here, so water is A, and the amine becomes the base. For the third reaction with formic acid and water, formic acid loses a proton, making it the acid, while water accepts that proton as the base. Track which species gains or loses exactly one hydrogen and one charge to identify conjugate pairs. Take your time working through each one. Here's the key relationship you need to memorize. When an acid is strong, it readily gives away its proton, leaving behind a very weak conjugate base that won't take that proton back. Think of it as the opposite. Strong acids produce weak conjugates. The same logic applies to bases in reverse. A strong base holds onto its extra electron pair tightly, so its conjugate acid is very weak and reluctant to donate a proton back. These are inverse relationships. Strength on one side means weakness on the other. This principle helps predict which direction acid-base reactions favor. Now we're introducing amphoterism, substances that can wear two hats. An amphoteric species is flexible. It can donate a proton like an acid or accept one like a base, depending on what it's reacting with. Bicarbonate, HCO3s, is a perfect example. When it meets a strong base, it donates its proton and becomes carbonate. When it meets a strong acid, it accepts a proton and becomes carbonic acid. This dual personality is crucial in buffering systems and explains why certain species can shift behavior based on their environment. Now we're moving to neutralization reactions, where acids and bases actually cancel each other out. The key insight is that while the molecular equation shows HCl plus NaOH making water and salt, the net ionic equation reveals what's really happening. The hydronium ion and hydroxide ion combine to form water molecules. That's the heart of every neutralization. For your example, HNO3 plus KOH follows the same pattern. Proton from the acid meets hydroxide from the base, they form water, and the leftover ions create potassium nitrate salt. Can you predict those products? Now let's apply the pattern we just learned. When nitric acid reacts with potassium hydroxide, you follow the same framework. Acid plus base produces water plus a salt. The key is identifying what salt forms. It's made from the anion of the acid and the cation of the base. So HNO3 gives you the nitrate ion NO3 mens, KOH gives you potassium Ks, and they combine to make KNO3. This shows you can predict neutralization products without memorizing every reaction. Just remember the general pattern. Now it's your turn to practice what we've learned. You have two neutralization problems to solve. For each one, identify the acid and base, then apply our pattern. The anion from the acid combines with the cation from the base to form the salt product, and water is always produced. Remember to balance the equation so you have equal numbers of each atom on both sides. Pay special attention to problem B. Calcium has a different charge than potassium, so you'll need more hydroxide ions to balance it. Try both problems, and we'll check your work together. Here are the complete balanced equations you should write. For problem A, potassium hydroxide and hydrobromic acid combine, with K-pis and Br-mans forming the salt potassium bromide. Since potassium has a +1 charge and bromide has a -1 charge, a 1-to-1 ratio works perfectly, so no coefficients are needed. For problem B, nitric acid reacts with calcium hydroxide. Notice calcium is +2, so you need 2 hydroxide ions from the base and 2 nitrate ions in the salt. This is why we add the coefficient 2 in front of HNO3 and H2O to balance the 2 OH mens groups from calcium hydroxide. We're moving into section 14.3, where we'll develop 2 new skills. First, you'll learn to recognize conjugate acid-base pairs. These are molecules or ions that differ by just one proton. When an acid donates a hydrogen ion, what's left behind is its conjugate base. Second, you'll predict the products when acids and bases react. Building on the balanced equations you just mastered, You'll now apply that knowledge to figure out what forms when any acid meets any base, using the same charge balancing rules we practiced. These are your two learning targets for section 14.3. The first criterion asks you to take a complete acid-base reaction and label all four players: the original acid, the original base, what the acid turns into, its conjugate acid, and what the base turns into, its conjugate base. The second criterion is your application skill. When I give you just an acid and a base separately, you'll write out the complete neutralization reaction showing what products form. Both skills build directly on conjugate pair recognition and balanced equation writing,